Bismillahirrahmanirrahim. Assalamu alaikum. Today we are going to start lecture number 10, and in this lecture we will discuss about the data transfer, add and subtract and those flags in assembly language, and we will implement those instructions inside assembly language, and we will see what is the behavior of those instructions inside the assembly language. This lecture is the continuation of the previous lecture. Previous lecture we discussed the theory about all and examples of these instructions, and we will see what we did in the previous lecture, and then we will start with the programming in assembly language and Visual C++. This is the review of the lecture number 9. You can see we discussed about the operand types, instruction operand notation, direct memory operands, move instructions, zero and sign extension, exchange, direct offset instructions. Here you can see we also discuss about the direct memory operands, where we have some example, like we define variable and we just refer that variable in the move and other instructions. We can use this direct memory operand inside the add and other instructions. Then move instruction with the memory operands. There are some different versions how we can use and how does it affect when the sizes are not similar of the operands. Then we also discuss about the data operands when we use permissible data operands, like we cannot transfer data from one operand to the segment registers, and also we cannot perform exchange or transfer or move between two memory operands. So the register operand should be there, or permissible registers should be there. So like this is the review from the previous lecture. So there were some errors why we cannot transfer, and we also did in the zero extension and the sign extension examples, and we will see the zero extension and sign extension in assembly language. What is the effect of zero extension and sign extension, and we will do some examples. Now we are going to start with the implementation or observation of all those instructions inside the assembly language. So here we will see this is the skeleton program. I want to increase the size, or maybe I can put it 135%. Okay, so this is the skeleton program, and now we will analyze all those instructions and these concepts that we discussed in lecture number 9. Here in the data section, for example, if we use count is the variable, and we use byte, count is a byte and its value is 100, and then we have the val or wval, and this wval is also is of type word, for example word, and its value is 2. Now these are the two memory operands, count and byte, so it's better to write byte in the capital to show that it's the reserved word. And now here we will write the code, like for example if I say move bl comma count, and then if I write move then ax comma wval, and if I write the move count comma al. So these are the three move instructions. Here two are count and mval. These are the memory operands. So now what we are going to do, we are going to see what's going to happen when we execute these instructions. We will increase or we will extend this program. So first what we will do, we will build this one, and after build Okay, so there are two errors. We'll build again our clean build. So we just start with the clean build. So here after clean build we have the output. The output is this one. I can show you this output in some format so that you can visualize. I just copy because it is I can reduce the font and you can see the output. So this was the output. Clean started, project example 2, configuration as debug win32, and 1 succeeded, 0 failed, and 0 skipped. So this is the output of this build, and now we are going to execute this one. Before that one, even you can check the properties before going to start any properties of this project. So this project is, but before starting this one we have to see build executions. MESM should be there, and then after MESM we have to see the references. So we have to see for this one, this is the build extensions, properties, Visual C, and these are the configuration properties, and so on. We just save this one, we just build again. So this is the build, clean build, and if I just execute, okay, okay, we just remove, for example, this one. Okay, so there's a problem with the linking because linking is not going to happen here. So we have to see the properties, but it doesn't show here the extension for this. So we just close this one, we just close solution, open a new project, is Win32. The name of this project is example 2, and we just have the create a subdirectory and so on. Okay, so we have the empty project. We just finished this one. We have project properties. Before that one we will have the build customization, MESM support, and we add existing items in the desktop, lecture number 9. We have example number 2. So this is example number 2. We just set the properties. You have the Microsoft Assembly, and here first we have to check the path. So the path should be there. It should be C drive masm32 include directory. Before that, you want to check the document, the computer, my computer, where is masm32, and is there any include directory. So there's include directory here. So all these files that we will include, they are inside this one. So what we will do here, we will save this project, we apply, and okay, now we will build this one. So you can see here the program this is the 100, and I will increase the font size so you can see this whole program. So code started from here. We define 2 memory operands, and we have three statements, move BL, and we have the one operand is the count memory operand, and then we have register operand. So what we will do, we will build the solution and observe this. So one build, 1 succeeded, 0 failed, 0 update, and 0 skipped. And then what we will do here, we will start the step-by-step debugging. So here you are going to watch the values of EAX 32-bit register. These are the values for 32-bit registers right now, and then I will just choose also show you all these. So EAX is there, then we have EBX. So we are utilizing BL and AX. So just watch these variables very carefully, that what are their values. And sorry, I can make it more small. I can make it float, so I can put it here near the code. So currently the value for BX is equal 7EFDE00, and ECX is equal 00, and so on, and AX is equal 76, and so on. If I just move to the next instruction, and now the count value, whatever the count value was, it has been a byte value. It was in decimal. So byte value in decimal is transferred to the BL. So BL is the 4-bit. BL is 1 byte value. So 1 byte value 100, and this is 32-bit register. So 32-bit register, and BL is 8-bit register. So this is the value which has been affected. This is the only 1 byte which has been affected, and its value is 64. And the next instruction, so EBX is 32 bits. Here BL is 8 bits. So only these rightmost 2 digits will be affected. You could see the previous value, and now it has been changed to 64, these 2 bits. Now if we move, you can see AX. So these 4 hexadecimal digits, because EAX is 32 bits. And here what we have to do, we have to change, or we have to observe these 4 digits. Then if I run again here, the value 00, this 2 in decimal is same as 2 in hexadecimal. So 2 has been moved to this EAX. Rest of the register, upper or higher order 2 bytes, they are still the same. So if we say move count comma AL, if I say count comma AL, now the value of count is same as the value of the AL, and then whatever the value of AL, now AL is equal 02, AL is equal 02, and then this is the end of the process. So what we have observed here during this code, that the values, the memory operands can be used inside the move instruction. Now we will move that. If I want to, for example, if I say move is AL comma WL, and if I say move AX comma count, then what will happen? Now you have to observe here that WL here is 2 bytes or word size, and count is 1 byte, and we are trying to move 2 byte value to AL, and we are trying to send or move 1 byte value to 2 byte register. Now just we are going to build solution. So here you can see the errors. Error 2, the instruction operands must be the same size for the first one. The next error is instruction operand B must be the same size. So these are the 2 errors that we got. That error was instruction operands must be the same size. So this was the error that we got in the in our program. So what we can do here, if I just rewrite this one in the same manner, if I say AL is equal count and AX is equal WL. So this is one solution, and I can just rebuild again. So project and clean build. So now it's successful. So the value here is operand's name is different. So again, what we do, we will clean build, or we first build solution. We just build solution. So it's 1 successfully built and 0 failed and so on, and we are going to start. Now initially just observe these values because BL is being changed. So right now these 2 digits represent BL. These 2 digits represents BL, and if I step forward, so these 2 digits have been changed for the BL, and these 4 digits represent BX, and all these 8 digits represent EBX. So what we can do here, if I run again or step forward, means step over again to the next instruction. So the contents of AX, these 4 digits, the contents are 3665. They will change to 0002. If I say move count AL, so the value of count at the location, like the previous location for the it was so now you can see the location for the count, count has been changed and its value became 02. And now if we move towards the next instruction, so count is equal to count has been transferred to AL. Now count value was equal to 100, but now count's value is equal to the lower order byte 2, so it has been transferred to AL. So again the value of AL is equal to same, is equal to 02, and AX has been transferred with W. Well, if I step over, you can see the value of AX is equal to WL. So value of AX is equal to 2 also. So now you can see here that we can perform move in the same size operands if it is not permitted to operate on different size registers. What we can do here, we can just finish this one. So it has been finished, and so what will happen if we write a program like this one? So you can check either they are permitted or not. So you have already seen that these operands are permitted or not. So what is the solution? If we want to transfer different size like smaller size to the larger size operands, then how we can transfer? The solution is zero extension or sign extension. First we will observe with the zero extension, then we'll move to the sign extension. Here you can see move BL, and first is the move BL. We can use, we're not using count, we will use only 1 0 0 0 1 0 0 and then 1 1 1 1 4 and 5 and so. Okay, so this one is the binary value. So if I say move sign zero extended, so move is the zero extended, so move ZX, and the value is, for example, if I say BL, so I just save this one and rebuild the solution. So I rebuild the solution with success. Just run this again. Now here you can see we did not get any error because BL is even though BL is 8-bit and AX is equal is 16-bit register, because we use the move zero extended. Now here you can see currently the value in BL will be updated. It will be 1001 and definitely it will be 9 and F. So 9F you can see has been updated in BL, and this 9F will be padded, or it will be added 2 zeros at the lower most significant byte, and value will be updated in the EAX. If I run this, so 009F, the value has been updated inside the EAX. Even the EAX, or you can say the AX part of this EAX. Now for example, if we want to use the value for next value, if I say move AX comma 0 1 0 1 hexadecimal. This is not the 0101 in decimal, this is hexadecimal, and AX is 16 bits, so 4 digits they can show 16 bits. Or maybe I can use FFF in hexadecimal, FFFF in hexadecimal. What is the error here? What is the error if you use this one? The error is if you're using any hexadecimal number whose starting digit is a character, so you have to use 0 here. So what I will do here, I will save this one and I move EBX comma move 0 extended EBX, 0 extended EBX to what I will move in 0 extend EBX, I will move AX. So here AX is 16-bit and EBX is 32-bit. So I will just save this one. I will just rebuild. Yes, I want to stop the debugging process. I want to rebuild again, so it has been rebuilt. I just start debugging right now. So first instruction is move BL. So this is the operation. BL will be 9 and F. So the value of BL will be 9F. Now we are at the second statement, our second instruction, move ZX, or 0 extended value for this 8-bit to the 16-bit. So value of 9F will be moved to this one. And now AX we are going to update or move the value. This is FFFF value is appended, added or moved inside the AX. Now we are 0 extending the 32-bit BX B register. What we are extending, 0 extending this value 0FFF, which is inside the register AX. So here you can see, and now the value inside EBX is equal 0 0 0 0 and FFF, so on. So this is about the move and the zero extension. Now if we want to use sign extension is different than the zero extension. Sign extension retains the sign value. Sign value has been retained inside the sign extension. So for example, if I use move cx, or if I say for example bx comma move bx comma 0, or I can say bl, okay, al, yeah, or I can say ax is equal to t. Okay, so ax, the same value for the ax, I want to say sign extended ebx comma ax. So what will be the solution? Oh, sorry, I want to rebuild it again. For example, I want to save this one, I want to rebuild or build it again, and I just debug this one. So here first instruction BL, this is same, so contents of this register, B register, will be 9F, and then first two digits will be 9F, and then contents of the AX register means first four digits will be 0 extended, 009F, and then the contents of this AX are changed from 009F to FFF, and we extend 0 for this value and update inside the BX register, so you can see all these zeros and FF. Now we are trying to update the same BX register, EBX register, with this sign extension. So you can see the sign extension. If we use sign extension, the values will be F, 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 and all these F, F values, because the sign for this one was for the F, 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 they will be like this one, 1, 1, 1, 1 F, second F, third F, and so on. So this was the maximum, this was the value. There's one F more. So all these were the values for F, F, F. Now what will happen, we are extending the sign. This was the value, and this was F, and then next F, F, and F. So these were the four values. Now they are sign extended. Whatsoever the sign values, if it is 1, then all these ones will be added, and this value will remain same. This value will remain same. So if it was 0, like this value was like 0, 1 or something and so on, it was not negative, so all these would have been zeros, because to retain the positive sign. So we just end this one. Okay, so we just stop debugging. Now these were the examples about the move, sign extension, and zero extension. Now we are going to start with the exchange instruction. What is inside the exchange instruction? So I will just comment all these and move them to the memory, or our old memory, because we have finished this section or these instructions. So I will just skip them. So moved, I just saved this one, and what we are going to do, we are going to perform the exchange. Now how we can exchange? We have two memory operands. These memory operands are like word in hexadecimal, and for example its value is, name is val1, or label is val1, and it is of size word, and we have val2. Val2, its value is 200 in hexadecimal. Now what we are going to do here, we are trying to use them in the exchange instruction. How we can exchange? For example, if I use the word exchange, where ax comma bx, ax comma val1 and exchange sorry, this is exchange bx comma val2. So these are the two instructions. I want to exchange the value of ax with val1 and bx with val2. So I just save this one, I build the project. So this has been built. I just debug this one. Now first value or val1 will be exchanged with ax. So the value of ax is 36. Eax is all these 8 digits, but we are going to consider only these 4 digits. Is 3665. So it will be exchanged. Right now this value has been stored at this memory location. The value at this memory location is 002400, and this is the memory location where offset location where our data section is referring this value. So if I just say step over, so here you can see the value of this has been appended. 100 has been added, or not added but exchanged with the val1. If I just say display or the debug windows, if I want to see the disassembly, so here you can see disassembly. So val2 is at here at this location. If I show the code bytes, these are the code bytes for val1 and val2. Exchange val2, here there's nothing. Code bytes have the problem with the code bytes is it's going to show everything. So eax plus offset, so this is the val1, and this is for one instruction which we are extending right now. I just exit from this code byte right now. I will show you again. So this is the disassembly. I just removed disassembly. Don't show address. Show symbol names, no. I want to show toolbar, show source code, show address, no. And I just build debug window. I want to say disassembly or view debug window, and then so I just remove this one and start again. So this was the value that has been stored, and now if I say I want to extend with the val2 with the bx, so bx has been extended with the val2. Now if we can refer the CPU the segment registers, and if we refer again these two values, for example, if I say move bh comma c val1 move, sorry, this is move, and if I say move bh or bl or bh with val2 also, just to see that what is the result, not the result but the, inside the memory, what are these values. Okay, sorry, it should be bx not the b, it should be bx because we made the mistake. It cannot be transferred. Val1 cannot be transferred to the 8-bit register, so we just debug this one again and start here. So the value of at this memory location 0125400 is 100, and what we are going to do, we are going to exchange this one. This is a next location, so its value is already 200. We did not modify this one right now. So what we are going to observe here, or what we observe here, is that AX its contents have been exchanged with the val1, and now we are going to exchange BX with the val2. If I just step over, then BX is equal to BX is equal to 2000, and here you can see 3665 is again the contents at the previous location. Or the value or the memory location where val1 has been stored. So now the new value which has been stored at that location 125400 is 3665, because 3665 you can observe here again. I just start here. 3665 is the value which is stored at the AX, So at this AX 3665, when we execute, so 3665 has been sent to the location or exchanged with the location of val1. That was the location was previously the location was different. Now the location is 944000, and for the val2 the location is 944002, and the value which is stored is 200 and 0, so on. If I step over again, this value has been for the val2 has been stored or exchanged with this EBX. Now you can see at the 944000 this location value 3665 is available there. If I say F10, press F10, and if I just move over, I step over, then you can see this is the new value which has been exchanged with the BX. Now previously BX was 200. Now the new value for the val1 will be 200 and 0. Now this was about the exchange. So this was the discussion about this exchange and move and all these instructions. Now we will talk about the direct instruction, direct offset operands, or direct offset operands. So what I will do, I will just keep this code in the memory or somewhere else. I just save this one. So now we will talk about the direct offset operand. Direct offset operand, we will use this direct offset operand in the arrays. So before using these direct offset operands, what we will do, so in this one first we will define the array. If I say array B or array byte, array B is byte. Either I write byte in capital or small, doesn't matter, but for the naming convention or like the programming practice, I'll write it like in capital. So 10H, 20H, hexadecimal, 30 and 30 hexadecimal, and 40. Okay, so this is array B and this is array B, and I want to use direct memory and direct offset memory accessing or direct offset operands. So for example, if I say move AX, or not AX but AL, move AL comma 10H, not 10H, sorry. If I say array B, and then the next instruction is move AH comma array B, but this notation I will try to make it different. So the value of array B, same value has been moved toward inside the AL. The same value I want to move in AH. Next I want to move AL with the value is array B plus 1, array B plus 1. So this is the next element which is stored at this array B. It will be sent or moved towards the AL. Just I store, save this one, rebuild the solution. If I rebuild the solution, then 1 succeeded, 0 failed, and 0 skipped. I just run this one again. Here you can see we have 10 at this memory location A8400. So A8400 is the address or in the offset in the data segment. So 10 is the value which is stored, because we are going to refer this value inside the array B, inside this instruction. It is shown by the array B or the starting address of this array. If I say 10, so here you can see the first initial value of this AL is 65, so it will be changed to 10, and AH is 36, and it will be extend with the 10, so it moved with this first element of this array. And if I say array B plus 1 will be moved inside the lower order byte of 16-bit accumulator register, or these 2 bits will be changed with the value is 20, because this is the second element of this array, and it will stop its execution. So you saw that if we wanted to access this array elements by using the direct offset scheme, so we did the same. Initially here AL became, or the AL AX whatsoever the value, AX whatsoever the value was, I write XX, and it will be 10 in hexadecimal. After that, after execution of this AX and the AX, it became 10, and this part has been changed or moved with the new value. And the next thing that happened, this is hexadecimal, and what we did again AL, so AX was equal to 10, and 10 now it became 1020 in hexadecimal. So this is about the how you can directly access the array elements by using the direct offset operands. There is one example. After that, now we know that there is exchange, there is also move instruction. Now we want to use these statements to exchange the array bytes, arrange the array bytes in this order. Like the array bytes should be in the order of 0, 1, R1, 3, 1, and 2. This should be the order of array bytes. For example, I just copy this one, I write it here in the comments, desired order of array B, it should be 3, 1, and 2. These should be the values 3, 1, and 2. I say 0, 3, 0, 1, 0, 2, and so on. I just move this one. I say if I were define in double word, D word, it should be better, so that it it will occupy whole memory. If I say the value, first value is 0, first value is 1 in decimal, then first value is array B is equal double word, then first value is 1, then we have 2, then we have 3. All these values are in 1, 2, 3, they are in decimal right now, so it will automatically convert them into hexadecimal instead of adding all these 0, 0, zeros in hexadecimal. So we just write it as it is. So if I say, for example, I want to move or arrange them into this order, first thing is I just move AX with the move EAX, because if I want to use 32 bits with array B, so the first element, or I can use this one to make the presentation more, make the presentation of this one more synchronized or similar. So if I say exchange with EAX comma array B plus 1, this is plus 4, for example. Plus 4 means the second element, because now we are using double word, so plus 4 is the second element. And then if I exchange with the EAX with the, now the value of EAX is equal 1, and what will happen, now I want to store the exchange with the array B and the 8th or the third element, and then in the end I will just move array D, array B comma EAX. So this is the end of this program. For example, for the convention to represent what is the value at the first array, I will just write one, for example, move AX EAX comma array B, then you will see what is inside this first element. So, okay, and for example, if I say move EAX EBX comma array B plus 4. We will see when we will use the display statements how to display results and so on, and that lecture it will be easy to display all those results. Right now this is the temporary solution, ECX comma array B plus 8. So I just save this one, build, I just build this one, build the solution. So succeeded, rebuild solution is okay, to confirm, to check it again. So here move EAX with array B, I just step forward. So array B value is moved in the EAX. Now the second element of array is being used, and its value is stored at 1294004. Its value is equal to, it will be exchanged with EAX. Now this 2 will come into the EAX, and at this location 012940004 it will be exchanged with this one, or with the value of EAX F10. So the value has been exchanged with the EAX, but now we are watching this one, the third element location, because we are referring the third element right now. So this third element again will be exchanged. The value of the third element right now is 3. It will be exchanged with the EAX. Okay, just move this EAX. Now you can see here we are moving EAX with the array B. So EAX, the current value of EAX is 03. It will be moved towards the 01294000. This is the first element. So if I run this one, so first element has been moved, and I'm again referring the first element. So you can see here 01294000, first element, its value is 0003. So it means it has been moved. And now if I want to see the value next element is 1, which is stored at 01294004, and this is the third element, which I'm going to refer, and I want to transfer it in the ECX. So here you can see first element has been transferred to the EAX, second element has been transferred to the EBX, and third element has been transferred to the ECX. So first element is 03, second element is 01, third element is 2. So this is the this is not the exact how can I say, the representation of that one. When we will when we will learn about the interrupts or some statements that are being used to display the contents or display the contents of register or send output to the monitor or something. So we will discuss, and that will be easy to represent the output. But right now this is the temporary solution. You can see we transfer those values towards the registers to see what is inside them. Now add and subtract, you can see add and subtract or increment and decrement is very easy. Add, subtract, increment. So I have to stop this debugging process. I have to save this one. So what I will do here, I'm using array. Array size is, for example, byte. So array size is byte. Its value is, first value is 0FF and hexadecimal. Second value is only 0. Now we will see what will happen if we perform add or increment and decrement first. Then we will move toward the add and sub example. So first of all, if I say increment and the move, or no, first we will write the simple program for the increment decrement. So it's better to use double word because I want to see the effect or on whole double word, and the value should be 4 bits, 4 digits and 5 hexadecimal. It's not array B. I want to use DW1 and DW2. So this is another double word, and its value is equal to value is equal, for example, if I use this one as a word, so W1, and it should be, I want to observe the operation of increment and decrement on this word and double word. What will happen, because there are two parts, I will use the word and double word. So one memory location, it is word 4, and double word is the 8. So for this one and for these, so this is complete 8 hexadecimal. So now for what I want to do is, our naming convention, I can use W1 and W2 is okay. So I want to increment. If I say increment here in the code, if I say increment, so increment can be applied to W1, and if I say decrement in the W1, okay, And if I say increment inside the it's not the incr, it's the increment. So if I say increment w1 w2, decrement w2, and if I refer them again, or if I move those values, for example, towards the move ax comma w1, move ebx with w2. So now you can see, if I just save this one, build again, so build a solution, and it's done. At this point, memory location 00bd400, so this is the value, or the w1 value, which is stored at the 00bd400 and 100 memory location. So what I will do, I will just step over and it will be incremented, and this is the w1 which we are again using for decrement. So right now the same location, its value has been increased or incremented, and it will be now decremented, and we are accessing another one, w2. So this is the location for w2. First we are incrementing, so you will see the increment here. Now again we are decrementing, and you will see the decrement, and again we are referring the same the w1, so its value is 1000, and it will be moved to the ax. So here you can see at the ax, and for this one the value will be signed toward the ebx. So this is the end of the program. So what will happen here, if I want to see the effect on the register ax and the of the move instruction, in case if I want to use like for example, my world or my m1 is equal to byte, and its value is 0 ffh, and the value for this, the byte second one is 0. In decimal or hexadecimal, doesn't matter, so for both it is same. Now we are using increment, or if I say move al comma m1 and ah comma m1 plus 1, and then if I say decrement ah, and then I say increment al and decrement ax. So you can see the difference. I want to remove this one, then see what is the effect when I, sorry, there is one error. So the error is, there are 3 errors. Sorry, I want to build the solution. So syntax error, there is, I have used, sorry, I have to use move, not move, and it was incorrect syntax for this one, so I just build again. So right now it's okay. If you start debugging, then first one you will see here that m1 or ff value will be transferred here, these first 2 bits, 2 digits, so they have been transferred ff. Now ah will be appended with 00, so it will be 00ff for these 4 hexadecimal digits. Now decrement ah, we want to decrement ah. What will happen if we decrement ah? So ah 00, if we decrement, it will become ff. If we increment al, it will be 0 0. If we want to decrement ax means whole, it will be FEFF. FF. This is the value if we decrement. So this is actually we are decrementing the whole, how can I say, the complete AX register. So FEFF is the result that we got here, and we just close this one. So you saw the increment and decrement. Now what we will do, we will move towards the negate statement or negate instruction. So for example, if I write val1 is byte and its value is -1, val2 is equal to is word, is of type word, and plus 3276767. This is the value. And if I negate, if I say move al comma val b val1, and then if I say negate al, and if I say the negate val 2 move ax comma val2. So now you will see the effect of this negate. So I just build the solution, and if I run this again, so here you will observe the memory location. Here you will observe the memory location. So here the first value is f at this one, -1 is ff at 00bf40. So this will be moved to al. So this will be moved to the al. These two bits have been changed. And then if we move towards the next instruction is negate al. So if we negate al, it will be 0 1. So this is the negation. So al has been negated, it will become 0 1. And if we negate val2, directly val2, so val2 is stored at this point. We have negated val2, so its value, it was in hexadecimal, so again its hexadecimal value will be 8001. So val2 is at 8001. So this is the new value for the, so 8001 has been moved to the ax. So it is here, this 8001 in hexadecimal. This is the maximum value that can be the positive 32767 positive value. So it is here. So what we are going to say here, that we can use negate to change the sign, for this one, for the values, for the operands or their values. So after this one, so we want to have the expression evaluation. If for example, if you receive or if you have any expression, and if you want to evaluate this expression, for example, in the last slide or last lecture, we saw the expression is, for example, Orwell, or this is the evaluation, or this is the expression. Orwell is equal to minus xval plus yval minus zval. For example, we want to define, I want to comment this one. So this is the main objective that we have to cover, we have to solve. Orwell is, for example, a double word, D word, for example, all of them are D words. So I want to see the effect on the whole register, not on the part, is the word, and we don't know what is the value for the rval. We will calculate, and then xval is double word, and its value is, for example, 4. yval, the yval is double word, its value is equal to 9, and then zval is double word, its value is equal to, for example, 4 or for example 3. Okay, so we defined these three, but before that one I want to stop this debugging and then solve this. We have to solve this one. So first of all, we have to move the xval, move EAX, the yval, and then move EAX, for xval, then we have to negate EAX, then move EBX with yval, and move add, we subtract EBX comma zval, and the last second loss is add EAX comma EBX, and the third one is the third one and the last one is move rval comma EAX. So this is the final one. So we just built solution, run this one. First value is 004, which we are going to move in EAX, so we just move this one. Okay, next is equal negate, so this is FFFFC, this is the -4 value, -4. Now what we are going to, yval is equal 9, it will be sent to the EBX. Now third one is subtract, we have subtracted and the result has been stored in EBX, so result is equal to 6. Now we want to add EAX and EBX. EA is equal to -4, and now it will be added with this one, so the value is equal to 2. So after this one, we want to send the data towards this rval location. The results have been sent to the rval location, so 02 will be sent to this one. So these are the results. Now final result is inside the EAX and also transferred to the location where rval has been stored. So this was the solution, how you can resolve these or solve these expressions. If you have some mathematical expressions, what is the way you can resolve. We also discussed about the carry flag, sign flag, and all these flags in previous slides. So now I will give you a brief overview inside the assembly language, how we can monitor them, those registers. For example, if I write, for example, move EAX comma EX comma -1, and if I said EAX with -1, if I subtract EAX 1, okay, then what will happen? If I just build this one and debug this one, so I want to show the flags. So here you can see the list of flags. So we have the overflow flag, we have the carry flag, auxiliary carry flag, and the other flags are there. If I run this one, so we have moved this one -1 to EX, so we have the 0 flag and this flag. 0 flag is equal to 0, and this flag has been changed to the 1. So PL flag has been changed to the 1. So you can see this is the for the sign. So this is the 0 flag. I think the -1, and we don't subtract. For example, if we add, I just stop this one, and EX was equal -1, and we don't subtract, we add EAX. So these are the two instructions. If we add these two, if we build, so this is the program. Building is complete. So move EAX, it's -1, and we add EAX, and the constant value is 1. So we just start debugging in steps. First we have to move. So FFFF, this is the -1 value that has been added. Next one is we want to perform. So carry flag is the auxiliary carry is here. So carry is there, auxiliary carry is here, and 0 flag is also 1. So carry, auxiliary carry, and 1, they have been changed. So 0 flag is also 1 here, and so on. So rest of the flags we will check when we will move towards the other operations. So this is end of the lesson, and hope to see you inshallah in the next lesson. Allah Hafiz.